In this work, we present a new visual localization method based on NERF for robotics application. We call our method CROSSFIRE, which stands for Camera Relocalization on Self-Supervised Features from an Implicit Representation. This is joint work between Huawei Paris Research Center and MinParis PSL University. We aim to localize a device by estimating in real time its camera pose in an already known environment. Usually, this environment is represented by explicit representations, such as a 3D point cloud of visual descriptors. This representation has a limited scalability when the reference data is abundant. Our goal is to develop an algorithm that instead uses NERF as the map representation. One current solution to use NERF for localization is to optimize the camera pose parameters with regard to the photometric error between the query image and the rendered image. However, it requires backpropagation through NERF at test time, which is very slow, and it is not compatible with real-world dynamic environments. Alternatively, Lens uses NERF to render a large training dataset of synthetic views uniformly distributed across the scene. It makes pose regression models comparable to features-based approach. However, the offline computation is very long and the accuracy remains limited. In our proposal, we integrate local features in the NERF implicit formulation. Given a camera pose, we render descriptors images through volumetric rendering. Hash encoding from instant NGP are used to accelerate the rendering, and appearance embeddings enable to train on dynamic scenes. Importantly, we make our descriptors invariant to the viewing direction to enable robust features matching during the localization. We train the neural renderer jointly with a CNN features extractor. We define a self-supervised objective to learn scene-specialized descriptors. The NERF geometry is important in our pipeline, so we use SSIM and depth total variation losses to improve its accuracy. Given the descriptors from an image and those rendered from the corresponding camera pose, the first term of a loss function asks them to be similar. In addition to that, we sample random pairs of pixels and enforce their descriptors to be dissimilar if their relative 3D distance is large. You can observe in the figure the matching scores produced by our method. The query pixel on the shelf matches with similar areas that are closed in 3D and presents low similarity with the rest of the scene. During deployment, we render descriptors from a pose prior and perform dense features matching with the query image. Because the depth of the rendered pixel is known, we obtain 2D 3D matches from which the camera pose is computed with the PNP plus RenSAC algorithm. While traditional methods stop here, we can refine the camera pose by rendering descriptors from the new estimate and reiterate the process. We compare CROSSFIRE to other NERF-based methods on indoor and outdoor scenes. We obtain a better median localization accuracy, especially on indoor scenes when the scene geometry learned by the NERF is more accurate. Here is a visualization of our results on the 7 scenes dataset. Query input images are on the right columns. Other columns display the colors, descriptors, and depth maps rendered by CROSSFIRE. When the camera pose is correctly estimated, rendered images are aligned with the query. We observe that, starting from inaccurate priors, our method produces pixel-level alignment with the query image, which corresponds to a centimeter-level accuracy.